Deadlock is an important condition of which programmers should be aware and have some understanding of how to prevent. So let's get to it. Five philosophers is a way of expressing deadlock without using a computing context. If you look at this image, there are 5 plates and 5 forks. If a philosopher sits at each plate, there would be 5 philosophers. But in order to eat, each philosopher requires 2 forks. That means all of the philosophers can't eat at the same time. You'd require some type of system in order for each philosopher to eat their meal. Now we can think of various systems, various algorithms to allow each philosopher to eat. And this is kind of the problem that we are solving. What would happen if all the philosophers tried to eat simultaneously? Nobody would be able to eat because by definition you could only grab one utensil each, so they'd all grab one and they all would be unable to eat, which is not a good situation, and you'd be in a deadlock because no one can eat, no one can finish their meal, and nobody would be willing to drop their fork at any point. So here's another way of expressing deadlock in more of a common programming situation. You've got a couple of processors, might be on a machine that's running, say, Windows, and those processors represent, say, 2 different games. Each loads up pretty much at the same time and grabs a resource. One grabs a video resource, one grabs an audio resource. But neither can properly load until they have both the video and the audio available. So each will try to get the resource it is missing while holding on to the resource it has. And it will not let go of the resource it has until it has both resources and completes its task. Neither process will ever release its resource. So each process will continue waiting for the resources it is missing forever. This is an example of deadlock. Here are a number of ways that you might try to avoid deadlock. The first one seems silly, just ignore it. This isn't the same as just ignoring it and hope it goes away. Well, you could have a poor operating system that doesn't handle deadlocks, but I think in most cases we're past that. You might have an embedded system, something like a cache machine, where each resource is managed by a single, let's think of it as a single process, or that system knows how to manage each of the resources such that the deadlocks will never occur because it only does one thing sequentially at a time. So ignoring a deadlock in that case might make sense. Back in the real world of programming, if a deadlock's detected, you might be able to roll back the state until the process can carry on, perhaps on another path. So this could be done with terminating processes that get caught in deadlock, or preemptively knowing, so the operating system might detect a deadlock could occur and preemptively stop a process or close it down. Other alternatives could be just to prevent processes hogging the resources. So you might mandate that a process, instead of holding on to a resource, just uses it when it requires it. If it can't get all the resources it needs to do the process, it drops all of the related resources. So you never end up in deadlock in the way we've described. Another way could be to have some sort of queue to manage requests for resources. So processes request in advance. Now, It starts to get complicated how even two resources might get their requests and how these might be ordered to make sure deadlock doesn't occur. And it's a possible application of Dijkstra's algorithm to try to sort out that problem. That said, it's complex to do something like that and have a queue, but all of these solutions are relatively complex, well, apart from ignoring it, and generally speaking, we don't ignore problems like this. Deadlock is a very real programming issue. Because computers tend to run more than a single program, yet still have limited resources, say a single speaker or camera or disk or disk drive, programs need to compete for these resources, and they may try to use them at the same time, which might result in a crash or a waiting state. Imagine if you're loading a program and it never loads because something in the background is using the disk. It's obviously not an acceptable situation. Deadlock isn't good for the user, it's not good for the program either, and so as programmers, we should be aware of that. Anyway, hope this video has been of use to you. Maybe see you next time.